Welcome to the first in a series of short videos on types of organic molecules known as stereoisomers. Stereoisomers, first of all, as you've learned previously, are isomers, essentially meaning compounds that have the exact same formula but are put together differently. As opposed to structural isomers, stereoisomers actually have the same structure as each other. They only differ in the arrangement of the atoms within that structure. As you will hopefully see in this series, this is an interesting study, not just for the understanding of chemistry, but for science in general. Stereoisomers are common in biomolecules. They're essentially the building blocks of life. And the story of stereoisomers starts with the discovery of their unique physical properties. Specifically, stereoisomers, pairs of them, are able to bend light in opposing directions. This ability arises from the fact that stereoisomers have a chiral center. Again, as you've seen previously, chirality requires an sp3 hybrid carbon, meaning a carbon with 4 individual single bonds. That carbon has to have 4 completely different groups attached to it. For this case, we'll just call them A, B, C, and D. And they have to be mirror images of each other. As one rotates the molecule around, you see that A and B, in this case, are occupying the same position, A being in the back of the molecule, B being in the lower quadrant, while C and D are opposite to each other. It's essentially like looking into a mirror and seeing the person on the other side raise their left hand when you raise your right hand. Now, this leads to the ability to bend light due to the fact that covalent bonds are polar. As long as you have dissimilar elements in a bond, there's going to be a difference in electronegativity, with the electrons drawn towards the more electronegative element. So, for our examples, let us suppose that carbon is the least electronegative element, and constituent D is the most electronegative element. At that point, the electrons would be being pulled away from the carbon and towards the constituent groups, but they'd be being pulled closer to D with a stronger force than they would to A with the weakest of the forces. What this disparity creates is an asymmetric electric field. In other words, the electrons surrounding the carbon are no longer evenly distributed. They're actually being pulled strongly to one side, towards the side of the constituent D in this case. This affects light in the following manner. Plain polarized light, or light in general, is an oscillating electromagnetic field. If that light is polarized in a plane, in X, Y, and Z space, it simply means that the electric field, the light in time, will create a sine wave in the XZ plane, and orthogonal to that, in the XY plane, there will be a magnetic field generated. The important thing is to see that these fields oscillate and they form a sine wave. So, when one electromagnetic field of the light interacts with the electromagnetic field surrounding an asymmetric chiral molecule, the following will happen. Those fields will interact. In one case, the stronger field is to the right, so the light will bend in a clockwise direction. This is called the positive optical isomer. In the mirror image, the stronger electrofield is to the left of the viewer, so the light will be pulled in a counterclockwise direction, forming the negative optical isomer. The formation of was the discovery of these isomers is the basis of stereochemistry. They're also important biomolecules. For instance, if I have a clockwise chiral sensor and a counterclockwise chiral sensor, I can add them in series. In other words, clockwise with clockwise with clockwise with clockwise, as you note, creates a spring or a helix. Similarly, counterclockwise with other counterclockwise also creates a spring going in the opposite direction. I now have two helixes, otherwise more commonly known as a double helix. This is the basis for DNA and RNA. Additionally, these stereoisomers that have handedness, one can go to the left, one can go to the right, can be added alternatingly, counterclockwise, clockwise, counterclockwise, or in any various combinations. This is the basis of the enzyme-substrate relationships. As you know, these two molecules will lock together and fit perfectly, essentially forming what is commonly known as a lock and key type of mechanism, where the alternating of clockwise and counterclockwise rotating atoms creates a pattern that can only be matched with its mirror image. So, one can see that optical activity is an indication of chirality. As a matter of fact, the discovery of optical activity, the ability to bend light, is what led to the realization that molecules can be handed, either left-handed or right-handed, and exist in pairs. The direction of the rotation, as you saw in this short video, is governed by differences in electronegativity between the substituent groups. However, some confusion arises in that the rotation direction does not necessarily indicate the structure, meaning that as far as naming the compounds go, which as you know is very important, the naming convention is actually governed by the mass of the substituents. So there can be instances where the name of an isomer does not necessarily match the direction in which the light is being bent by that. This will be explained and gone into in some detail in the following series of these videos. Thank you for listening, and I hope you enjoyed this video and found it useful.